Hello everyone. Today I am here to give a presentation on my Capstone project, which is a learning framework for deformable medical image registration. This is done by students of IIT Kharagpur and it is presented by myself RAMYASRI and the other participants in this project are SWARNIM and MANISH party. This is the flow of contents which we are going to follow in this presentation. Before going to the topic, I just want to tell what is meant by image registration. Image registration mainly involves aligning a fixed image with a moving image by determining the transformation that best matches corresponding features or the intensities between them. It's like you are mapping your moving image to the fixed image. This is the methodology which we are going to follow. Here you can see this is my moving image, this is my fixed image, this is my unit structure or a neural network which we are going to train, and this is my registration field. The registration field here is a two-dimensional vector which uses a displacement in the x and y direction. Now I am going to give this registration block and my moving image to the spatial transform block. The output of the spatial transform block is a registered image, which is nothing but the moving image which is mapped to the fixed image. This is a unit architecture which we are going to follow. Here what we are actually doing is, at a time we are sending the moving image and the fixed image to the unit structure. These images are placed in such a way that they are placed along the z dimension. And this is the architecture which we are going to follow, and the output, my input image is of the dimension 256 cross 256 cross 3, and there are two such images, so my total dimensions, when I keep these images along the channel dimension, then my overall dimension will be 256 cross 256 cross 6, and my displacement vector which we get from the unit architecture is of 256 comma 256 comma 6 sorry 2, which means it gives a displacement in the x and y direction. Now after I get my registration field, as I have already shown that my registration field and the moving image are given to the spatial transform function. Spatial transform function, what it actually does is, for each pixel location p, we calculate the corresponding pixel location p dash in M, and the value at the p dash in the moving image I found it by the linear interpolation. The formula of the linear interpolation is given here as follows. The loss function which we are used here is unsupervised loss function, and it is mainly the addition of the similarity index and the smoothing index. For calculating the similarity loss, we are using local cross correlation loss. We can also use mean square intensity loss, and the other loss is smoothing loss. The formulas are as shown in the figure. Now, I conducted this entire method on my dataset, which is fire dataset, and the hyperparameters which I used here are given as follows. This is my model summary. It's the same unit architecture that I have already shown before. Here you can see my output dimension deformation matrix is of size 256 cross 2, where 1 here is the batch size. And these are the results: the moving image, fixed image, and the registration image. This registration image are the output from the unit and the spatial transform block, and the moving image and the fixed image are the inputs that we are giving to this uh, architecture, I mean to the unit, and the output I get from the spatial transformer block. And these are the results. Here you can see what I am actually trying to show is the registration error map, which is nothing but the difference between my registered image and the moving image. And here I included the checkerboard image. Checkerboard image is a metric which can be useful for displaying the results of the image registration. Hence, here what we have done is the image registration using CNN and the spatial transform block. Compared to traditional method, voxel morph works better than the traditional method. The time taken for this is low when compared to the traditional methods. These are the references. The first reference is the main paper that I followed for this presentation. Thank you. Now I'll show you the code of my project. As the like I am taking 89 image pairs for training and 45 image pairs for validation, and the running this, it is taking a lot of time, so I'm not running the code now and showing. I'll just show you the results which I got. These are the necessary libraries that I have used. As you can see, the cross correlation loss between the two input sensors, it mainly used to it increases the model to produce the output similar to that of the ground truth. And smoothing loss, I already said. And here I did not use this voxel morph and die-score loss. Here I am loading the data set. Here I am just taking my data set and I am loading it, and the batch size is 1, and here I took number of workers as 2. Yeah, when coming to the unit block, I have the contracting block, expansive block, and my bottleneck and the final block. The contracting block, what it actually does is it actually down samples, and then in expansive block it up samples. So in order to get my original image. Here you can see I used 3 convolutional layers and 3 max pool layers. In each contracting block, in turn I have 2 convolutional layers. And max pulling by 2, the kernel size is 2, and I'm taking stride as 2, or we can take it as 1 as well. The bottleneck is shown as follows, and the decoder which I used, this is my model. Like I use 3 encoder blocks, a bottleneck and the decoder. Here in unit we have the residual connections. It's like like the bottleneck and the encoder block are concatenated. Similarly, as shown here, the spatial transform block, it mainly consists of the following. First, it consists of mesh grid, which generates a 2D grid of coordinates based on the input height and width. And then we use interpolation, like bilinear interpolation, to estimate the pixel values at non-integer coordinates. It's a spatial transformation to moving image using a deformation matrix. The new coordinate perform interpolation and returns the transformed image. And this is my main voxel morph architecture, where what I'm actually doing is Unet. The output of Unet is given to the spatial transform. Here you can see deformation matrix is the output of Unet. Now I'm giving this deformation matrix and the moving image to my spatial transform block, and in return we will get the registered image. Here I used Adam optimizer, and number of epochs I kept it to 25. And these are the loss functions which I have already said. This is the training loss and all these things. And here we are plotting moving image, fixed image, and the registered image. Here you can see clearly that the my moving image is fixed, like it is mapped to the fixed image. These all are my moving image, fixed image, and the registered image. All these things. And this is my training and validation loss. And as I said, I used a checkerboard. This is the code to implementation of checkerboard, and these were the output results. As I have already shown in my PPT, that the error map between the moving image, between the registered image and the fixed image is as shown. That's it. This is about my project. Thank you for listening.